evening, everybody, and welcome to today's seminar. We should be starting in about 2 or 3 minutes, so kindly bear with us. We are getting some more people to join in, and we'll start very shortly. Thank you for your patience. Good evening, everybody, once again. Good morning to some of us. Good afternoon to some others who are from different parts of the world. My name is Commodore Sujeet Samaddar. I'm an advisor with MRAI, and it's my pleasant duty to be hosting this seminar on a very, very important topic on the options for decarbonization of the steel industry. There is increased urgency to attempt to curtail these emissions because the 1.5 degree centigrade target that is required to contain global warming seems increasingly elusive as every day counts. We all know that the iron and steel industry is a hard to abate sector. It has attracted the attention across the world to try and see how the 6% of global CO2 emissions that it makes, the 8% of energy related emissions that it makes are curtailed. So therefore, there is no doubt that this deserves the most urgent attention of not only the industry, but actually the whole of mankind. Yeah. These emissions are not sustainable, and we have to look for our future of our progeny, and we need to do things that will correct this situation. But of course, iron and steel are vital commodities for all of us, and I cannot imagine a world where we can do without iron and steel. It is a necessity of life. But we have to figure out how do we check out the optional decarbonization technologies, which will be discussed at length today during the seminar. And this requires, the consideration of ideas like hydrogen injection, solid biomass substitution, of course, carbon capture, utilization and storage systems, which can be retrofitted on many of the furnaces that we have. And of course, very, very important to see zero carbon electricity. But be that as it may, the blast furnace and the oxygen furnace still continues to dominate the production processes for steel, iron and steel in the world, accounting for 71%. In India, it is a lot lesser, but nevertheless, it is a sizable proportion across all iron and steel manufacturers in the world. Different techniques for direct reduced iron has been done. More and more, the electric arc furnaces are coming in. But of course, the challenge with electric arc furnaces is that we need scrap, and that seems to be difficult to get by more and more every day. So we need to figure out how do we get these adequate quantities of steel scrap, and once having got that, how do we use it optimally to reduce our carbon signatures? So today we'll be looking at options, and I'm sure our very, very erudite and very prominent speakers will give us some ideas on what the challenges are and what the potential solutions are. Some of these I hope will be discussed today, including the DRI-H process, which is what seems to be something that I've worked on a bit, and it seems to be a good option to be pursuing. Obviously, there are multifarious options, and I can go on for this all. But one thing I'm quite clear that these options are not one size fits all. It depends on each economy, it depends on each geographical area, and so on and so forth. But definitely the urgency is witnessed today. We have seen the COP28 declarations and the recent European Union notification on digital product passports, which has put iron and steel industry at the top of that list. So therefore, we are very, very fortunate that we have all gathered here to discuss this subject. And I'm very fortunate that I have two very eminent speakers who will be discussing these subjects. First of all, we'll have the first presentation by Sabarish, who is a program associate at the Council on Energy, Environment and Water, a premier think tank in India and a policy research institution which has done great work on this particular sector for the government. He's got a lot of experience on this. He's been focusing his work on steel decarbonization, natural gas systems, carbon capture and green hydrogen, on which we have had some very interesting discussions earlier. He has a degree in mechanical engineering from Anna University and a master's degree in sustainable energy engineering from the KTH Royal Institute of Technology at Stockholm. I'm also very privileged to have Dr. Sara Hornby here, who's been variously described as a trailblazer, rebel leader, and an inspiration for not only ambitious woman. She says ambitious woman, but I think she's an inspiration for all of us because she's continually proven that nothing is out of reach if you set your mind to achieve it. She was the first woman to graduate from Sheffield Hallam University. She has a PhD in industrial metallurgy, and she spent early years working for major companies like the British Steel Corporation and the Firth Brown Tools Engineering. She's worked extensively in Canada and US on air liquid rolls, and she has a lot of experience in EAF steel making optimization positions. She's a fellow of the Institute of Materials, Minerals and Mining, and was that 2022 Hatfield Medal and Prize winner. In 2022, she was the recipient of the Benjamin Fairless Award and the John Bell Award. In November 2023, she was awarded an honorary doctorate in engineering by Sheffield Hallam University. And we'll all agree that we are really privileged to have her here. Continuing this discussion forward, I'm also very privileged to have my good friend Zain Bhai here, who is a vice president of the Material Recycling Association of India, which, as most of our audience knows, is the premier recycling association of India, which has actually steered the recycling environment and industry in India. Zain Bhai is also the managing director of the Nathani group of companies and is one of the most renowned figures in the Indian recycling industry, providing guidance across all sectors of the recycling industry. He's also an alumni of the University of Virginia, and he shifted to India to pursue his career in developing the recycling industry in India. Finally, we'll also have Ritesh Bhai, who will be joining us later, who's also a director and a very renowned industrialist in India. With these opening words, just a quick few housekeeping rules for all our audience. I suggest that whatever questions you have, put them in the chat box so we can address them at the end of it. Number one, kindly keep your audio off during the course of the discussion so the background noises are reduced and we can actually listen to what our esteemed panelists have to share with us, and they have really taken time to join us here, so let us give them that respect. And with these few words, I now request Zain Bhai to say his welcome remarks and take the proceedings further. Mr. Zain Nathani, please.
Sure. Thank you, Sujeet Bhai. Good evening, ladies and gentlemen. Big welcome from MRAI. I'm the Vice President of the association, and it's a pleasure to be hosting this very important discussion of decarbonization of the steel industry. Personally welcome Mr. Elango and Dr. Hornby to this esteemed panel. Thank you very much for taking the time to join us. We all aware steel is the backbone of modern infrastructure today, from skyscrapers to bridges, automobiles to household appliances. However, the environmental footprint of steel production is also significant, and it accounts for almost 6 to 8 to 9% of global CO2 emissions. So this makes the decarbonization of our industry not just an option, but an urgent necessity. The rapid expected growth in steel output in India and globally would result in an increase in emissions from our sector, and they're almost expected to double by 2030 in a business as usual scenario. So it's very, very critical that this sector adopts low carbon means of production at the earliest, and gradually shifts to carbon neutral pathways, finally, which will lead to producing green steel. This presents a massive decarbonization challenge for the Indian steel industry and the world at large, but also provides us with a massive opportunity. And we at MRAI are committed to promote sustainable, circular, green steel production. Considering this vital necessity, MRAI has scheduled this international webinar featuring experts from government, industry, academia, all you attendees as well, so that we can learn a little more on some of the initiatives and the issues that are facing us today, whether that's transitioning to renewable energy, whether that's the economic viability and competitiveness of green steel, whether that's using competitive cutting-edge technology in decarbonization, and what policy support and industry collaboration can we actually work together to take things forward. So in conclusion, it's quite clear decarbonizing the steel industry is a significant challenge. It's one we must tackle together by increasing minimum recycled content in our everyday products, by utilizing renewable energy and fostering collaboration. We can build a stronger, more sustainable steel industry that meets the needs of today without compromising the future. I very much look forward to the papers by our very eminent speakers. who are going to ensue the deliberation, and so that we can chart out a suitable policy recommendation that we can actually then take to the government of India as well on how we can work towards decarbonization and green steel. I spent most of the afternoon today at the Ministry of Steel with very senior officials, and I'll tell you, everyone is talking about this topic right now. Circularity, decarbonization, green steel. They want more information. They want associations like us to take the lead on helping them on how we can work together to help the Indian steel industry as well. So with that, it's a very, very hot topic right now, and I really look forward to Dr. Hornby and Mr. Elango's presentations. Thank you very much.
Thank you, Zain bhai, for that introductory remarks. So first off, we'll request Mr. Elango to kindly make his presentation. I request Sufyan if you can give him the slide share and the rights to share his screen so we can get going.
Thank you, Commodore. And can you please confirm if you can see the presentation? Is it still visible, right? Okay.
Yes, go ahead, please.
Thank you. Hi, everyone. And first of all, I would just like to thank the MRAI for having me in this webinar. Thanks to Commodore Samaddar for the multiple backs and forths we've had on this topic and the invitation to me that was extended to me to even present here. The topic is like very vast, but then the simple question that we're trying to answer is how will or how can India's steel industry decarbonize? So my name is Sabarish Elango. I work with the Council on Energy, Environment and Water, which is a leading not-for-profit policy research organization based in Delhi. The Council's mandate is to impact sustainable development at scale with data, integrated analysis, and strategic outreach. Our research aims to bring about transformations in the economy, its energy systems, and livelihoods. It works to improve the quality of life for our fellow citizens, and it works on multiple enablers to bridge this gap. We have more than 300 people at the council, and we have more than 380 peer-reviewed publications. We have been engaging quite a lot with the central government, but of late, we've also been engaging with a lot more with the state governments for local policy making. We've been engaged in more than 20 states. I myself work with the industrial sustainability team, and I have been working on the steel sector since I joined CEEW in 2020. So about 4.5 years now, I've been working on steel decarbonization, among other topics. And our team has been working very closely with the Ministry of Steel in developing new policy for green steel production in the country. And we've been involved with deliberations and discussions with several committees within the ministry for the past 2.5 years, I would say. And so based on our research and based on what we know from discussions with industry, I would just like to make this presentation today about what the different pathways are and how and what likely pathways are going to happen for the Indian industry to decarbonize. Also considering that the country has set a net zero target for the year 2070, we don't have much time left. I'm sure everyone who's attending this already knows everything about the general pathways of steelmaking and stuff, but perhaps there are some who don't fully know. For the benefit of them, I'm just like having this short slide here where we're talking about the two broad methods of steelmaking. So the first one is using the oxygen route, where oxygen-based steelmaking, or it's integrated steelmaking as it's called commonly, where iron and metallurgical coal, which is also known as coking coal, they are melted together in a blast furnace, and you produce pig iron from this process. And this pig iron, along with some amount of scrap, some alloying elements, they are charged into a basic oxygen furnace, where you get steel from, where you control the amount of carbon that is in the iron, and then you get steel. The other process is called electric steelmaking, or DRI-based steelmaking. In this case, you don't melt the iron necessarily, but you reduce it under high temperature in a furnace, and then you get direct reduced iron. Here you can use any type of non-coking coal, like regular medium-grade coal, or there are processes that use natural gas as well. And the resulting iron is then melted in an electric arc furnace, or there's also another type of furnace called an induction furnace, which is not shown here. So an electric furnace is used to melt the iron that is produced, reduce the carbon content down to produce steel. So another interesting point to note here is that DRI can be produced with both coal-based processes and gas-based processes. However, it's not that the same piece of equipment can handle both coal and gas. They are very different designs. And similarly, we talk about hydrogen injection in the blast furnace and so on. We're really trying to retrofit existing designs with new technologies and fuels, and they can only go up to a certain amount before it becomes difficult to control the process normally. And there are multiple different pathways or routes of steel making based on how you combine the different technologies and types of raw materials. But we can broadly say that these are the two big pathways. Coming to the Indian industry, it's the second largest in the world. We have more than 150 million tons of crude steel production capacity, and we produced actually more than 120 million tons in 21-22 financial year. And the big story for the decade is that we plan to double our steel making capacity by the 2030s. So there's going to be a lot more steel coming out, which means a lot more coal and iron ore going in. So then the challenge is, how are we going to grow sustainably if this is how much our demand for steel is foreseen by the industry? In India, there are 5 major steel making routes that, as we see it. So there are some oddities. There are one or two plants here and there that use entirely different technology, but then we just combine them into the most relevant category for simplicity. You have the BF-BOF process, which, as I mentioned, uses iron ore and coking coal. You have the gas-based DRI and EAF. You have the coal-based DRI with the EAF. And then you have the coal-based DRI with the induction furnace as well, called the IF. And then you have induction furnaces that purely melt scrap steel and produce recycled steels from scrap. So the interesting thing about the Indian scenario is that the electric route has a higher share of final steel of crude steel production than the oxygen route, which is contrasted by the rest of the world. If you take the world average of steel production, more than 70% of the steel globally is produced using the BF-BOF route, and only about 30% is coming from the electric route. However, in India, there's an abundance of small plants. As you can see, there are only 52 blast furnaces and 18 basic oxygen furnaces in the country, whereas there are almost 300 DRI plants and more than 800 induction furnaces. So it speaks to the scale and the issue of scale, where you have large players being able to put in large amounts of capital to produce high quality like BF-BOF steel. But there is also an abundance of smaller and medium scale industries using the DRI and IF process, which is less capital intensive and does produce important steel, primarily for the construction industry, which is highly cost sensitive. Now, based on our analysis of the processes and the amount of raw materials and the types of raw materials that go into these processes, you can see the emission intensity of the processes on the table. So the DRI-IF process, which is primarily dominated by the small players, is obviously going to be the highest one, with around 3 tons of CO2 for every ton of crude steel that is produced. The BF-BOF process as well is quite emission intensive, around 2.5. Same for the DRI-EAF process. However, the gas-based DRI-EAF process is very much cleaner in comparison, about 50% lower emissions, around 1.6 to 1.9. And so that is a process that has a lot of potential when it comes to decarbonization, but that has its own challenges, as we'll see later. Now, there is an asterisk here where I say including some amount of BF ion. And this, I will just show you why that is the case in the next slide. Because while we do talk about processes in sort of compartments that, oh, this is BF-BOF, this is DRI-EAF, it doesn't work like that in practice. There are lots of combinations that industries adopt based on the equipment they have available, based on the quality of steel they want to produce, and how they control the processes with the plant. So if you see the arrow marked number 1, you see that some amount of ion from BF goes to EAF. It's not necessary that it's only a BF-BOF process, right? So this is because some plants also charge pig iron from the blast furnace into EAFs, primarily to reduce the electricity consumption in the EAF and also to somehow control the quality of steel that is coming from the EAF. And arrow mark number 2, you will see that some very small amount of coal-based DRI-EAF capacity is there in the country. This is primarily in large integrated steel plants that have multiple technologies within the same facility. So they will have a blast furnace, they will have a basic oxygen furnace, they will also have some DRI kilns, and they will also have electric arc furnaces. This is simply based on the economics, how the industry grew, what kinds of steel they produce, what grades of steel they produce. And so they mix and match the processes to suit their needs. And the third is probably more interesting for our cohort here on scrap. Every steelmaking process uses some amount of scrap. 10 to 15% of scrap is blended with iron when it goes into the steelmaking process. But this can go much higher, right? If we're able to recycle scrap, that's a win-win because we get rid of waste materials and we produce new steel without having to mine new coal, mine new iron ore, and cause a lot of supply chain issues. However, we don't have that much scrap available, as Commodore Samaddar mentioned in his remarks. A lot of the scrap that is used currently is actually generated within the plants themselves, because plants have finished steel production processes where there's a lot of cutting, blanks and all involved, where there's some amount of steel that goes back into their BOF or EAF. So scrap coming from end-of-life steel is still a challenge in India. And again, that is something we'll see later as to why that is. And based on the current configuration of these industries and the technologies that are available to us and the best case pathways that we can use to decarbonize, I personally see three major routes for how our industry could grow and decarbonize. The first route is to use existing technology, is to grow using existing technology of using coal-based BF, BOF technology, for example, which is what industries are primarily erring towards in terms of capacity expansion. Most of it is based on the BF, BOF technology that is coming in. So we can take this existing technology and we can deploy the best available practices and technologies for improving energy efficiency. We can put in better process control, more efficient drives and systems, better cooling mechanisms. All those things we can do. We can replace whatever power consumption that is there coming from the grid or coming from a coal-based power plant. We can replace that with renewable power, and then potentially also blend some amount of sustainable fuels with coal or sustainable raw materials with iron ore, and then reduce our reduce our emissions. But however, this is limited by the process. And then whatever remaining emissions there are, we go for carbon capture and utilization or carbon capture and storage. The second route is to deploy gas-based capacity, because the gas-based technology that exists for DRI and subsequent steel production can switch to green hydrogen incrementally. And there are companies who claim that they already have commercialized technologies that can use entirely green hydrogen for producing steel. So that gets rid of the coal problem, that gets rid of the coal to gas switching problem, which is a limitation in terms of the technology. So we used a technology that already uses gas and switched from natural gas or gray hydrogen and then to green hydrogen subsequently. And whatever other energy that comes from electricity, we switch that to renewable. So then we produce clean steel. And the third route, which is a scrap-based route, we look at how much scrap we can make available right now. We look at new avenues of scrap collection. We look at improving the logistics and delivery of scrap such that the system is more efficient and costs less. And then we use renewable energy and the best available technology for energy efficiency to sustainably and efficiently recycle scrap to produce new steel. Now here, you can notice that there's an asterisk, and I'm calling it clean steel and not green steel. I hesitate to use the term green steel because as of yet, while everyone is talking about green steel, nobody has really agreed on a common definition as to what green steel even means. So does, BF, BOF and using carbon capture on a BF, BOF plant, does that mean it's green steel? But you could argue that there are emissions from mining and transportation. Is hydrogen-based DRI and renewable power-based EAF green steel? You could say there are manufacturing emissions from RE. You could say there are the land use impact changes, water consumption, all those problems. So there are lots of issues, and there are multiple groups of stakeholders and people that are debating this issue right now. And the government of India is also yet to formally recognize a position on what they define as green steel. So I'm just going to call it clean steel for the rest of this webinar, and that is the reason why. Okay, so let's take the first route as an option. So if we look at the existing capacity and the existing technology, there is going to be a heavy reliance on carbon capture for decarbonization. I'll tell you why. It's because no matter how efficient you make the process, no matter how much amount of alternative fuels you try and blend, they're only going to go a certain amount of the way to decarbonize, right? Because this is an existing technology that is a well-established technology that has evolved for centuries almost. And there's only so much you can do in terms of augmenting an established process to reduce its emissions. You can't simply switch out coking coal for green hydrogen, for example, because that's simply not how that technology functions. You need to have some amount of solid fuel in that blast furnace so that the process happens normally, so that the weight of the iron ore is borne by that coal bed at the bottom. So that means that you can't simply replace a solid fuel with a gaseous fuel and try to reduce your emissions. And even if you switch your entire electricity consumption to RE, the electricity consumption is only a small part of the emissions coming from the whole process of steel making, obviously. So even if you switch your existing capacity to RE and put in 6 gigawatts of new renewable power, round the clock renewable power, and that round the clock is an important term here because steel plants operate round the clock, and you can't have a solar power plant producing the peak amount of power at 2 p.m. and then subsequently tapering off, and then you have to rely on the grid again. So you need a combination of wind and solar potentially, and some amount of energy storage, which means that while people keep saying that solar is already cheaper than coal at 1.8 rupees, 2 rupees, if you look at round the clock RE, the cost at the producer that the cost that the producers are quoting is around 3.5 rupees. So it's still quite expensive. And even if you do all that, you only get a 20% CO2 reduction. So EE plus RE plus alternative fuels, whatever you can blend in, it's only going to give you a 44% reduction for the existing technology base and for the existing capacity, that is. And the remaining more than half of the emissions, this means is going to rely on carbon capture and storage or carbon capture and utilization for abatement. Now, I said that 2070 is not far away. We're already in 2024, almost in 2025. We do not have any ecosystem for CCUS in the country. There are some companies doing small trials. There are some institutes that are doing some amount of research, some lab scale, some very minor pilot scale demonstrations that are going on. But there is no policy for CCUS in the country. There is no large scale development of reservoirs for CO2 storage. There is no large scale research either that's happening right now. And we also have looked at the CO2 sequestration angle. And best case, if we start aggressively looking at sites for sequestering CO2 in the country right now, and we go about it on a war footing, we can start injecting only 15 years later, right? So for the next, even if we start taking efforts right now, it will take till 2040 to even start injecting CO2. And that's for the entire country, not just this particular sector. So it's a very critical challenge that the industry faces in terms of its reliance on CCUS and hinging hopes on CCUS for decarbonization, especially when we have export restrictions, we have carbon markets, all these things coming into the picture. Will we be able to sustain for 25 years at 1.82 tons of CO2 when we should be already at below 1 going forward, so that we get past all of these problems and actually put an effort to decarbonize. And because there is no reliance, because there is no CCUS ecosystem in the country right now, it's going to cost a lot of money to develop that. With present day estimations of the cost of equipment for CCUS, it will cost us 21 lakh crore over the next few years to decarbonize the existing capacity only. However, if the cost of CCS declines, if it becomes $50 per ton of CO2 from the 90 or 100 that it is right now, we could potentially be looking at a bill of 13 lakh crores rather than 21. That is still a large sum of money, and we need to plan where we get the money from and how we will put the money into the ground to develop these technologies in the coming decades. And on this slide, I will not dwell too much, but what it's essentially saying is that if you try to produce clean steel, that is near net zero steel using existing technologies plus CCUS, it would probably be 40 to 70% more expensive to produce at current prices. And if CCUS, the cost of CCS declines from 90 to 50, it could be still 20% more expensive than it is currently. And that's not a small number. 20% is a lot. So we're looking at steel that costs 25,000 rupees to produce, that will become 35,000 rupees. So it has knock-on impacts in every other sector that uses steel. What about the second route? If we look at hydrogen-based steel making, well, we can do that. There is already a plant in the country. There are already a couple of plants in the country that use the gas-based technology. Let's say we take a shaft furnace, which is the gas-based technology to produce DRI. And instead of using natural gas, let's say we use gray hydrogen, right? Gray hydrogen is produced by reforming natural gas, and it costs much less than green hydrogen does. Let's say we start operating a shaft furnace using gray hydrogen, and then putting that ion into an electric arc furnace powered by renewable energy, and then subsequently blend green hydrogen into the process going forward into the future. What would that look like? I mean, like this chart is a little confusing, but the key messages are on the left. The new, as I said, the new gas-based furnaces are already capable of using green hydrogen. So we can initially run these furnaces with a combination of gray hydrogen and RE, which means that you would probably come to an emissions level of 0.9 or 1 ton of CO2 per ton of crude steel, which is right down the middle of that chart on the right that you see. And then subsequently, if you keep blending green hydrogen with gray, over time, you will reach 100% green steel in this case, or clean steel. And then the cost premium will keep going down through with time, because the cost of green hydrogen is also expected to reduce. So if you take a 2040 case, which is the dark gray line there, if you take a 2040 case where you blend 90 to 95% green hydrogen, you could be looking at emissions of only 0.3 tons of CO2 per ton of crude steel. Another interesting insight from this graph is that you will notice that if you read it from the right to the left, towards the very end, the prices go up substantially. And the reason for this is because if you want to produce 100% hydrogen-based steel, you will need to produce hydrogen round the clock, which means that you would need to have round-the-clock renewable energy. And that means that the cost of the need for energy storage goes up, which is the most expensive component. So if you want to blend 90% green hydrogen, let's say, then you can only do away with certain amount of storage and then have the rest coming from gray hydrogen. However, if you want to produce 100% green hydrogen-based steel, you will need a lot more marginal storage to deal with the vagaries of RE and its intermittencies, which drives the cost up. So this is also a strategy that we have to evolve with time based on how the prices of energy storage reduce, how the prices of green hydrogen production components reduce, and how we can effectively blend green and gray hydrogen in a shaft furnace. But having said all these complicated things, the point remains that if you want to produce virgin steel, it seems that the gas-based route is the most promising, because it is going to be a gas-to-gas shift from natural gas to hydrogen, and the technology already supports it, and you won't need to rely on CCU as that much here, compared to the previous case where too many hopes and dreams rely on an ecosystem that doesn't exist. And now we come to the third case, scrap-based capacity. Here, how would we go about augmenting the supply of scrap, and how would we go about supplying renewable energy to these people? As I said, 10 to 15% of scrap is charged with iron in all steel-making furnaces in the country typically. And importantly, more than 10% of the steel that is produced in India, it is produced primarily through the scrap recycling route. It is to be noted that these might not be very high quality products, but still it counts nonetheless. So India consumes 25 to 30 million tons of scrap annually, of which around 5 million tons is imported scrap, because we do not simply have the logistics to make domestic scrap recycling work to the scale that we needed to. And as I mentioned earlier, a large part of the scrap is actually generated within the plants. So you can't even say that it's end-of-life steel, that it counts for zero emissions. There's a lot of scrap also generated from shipbreaking in India, India is, I think, one of the world's largest shipbreakers. And formalize that sector such that large amounts of steel scrap are available from a particular location, which makes transport and logistics cheaper. So how would we augment supply? I mean, shipbreaking is something we already discussed, but the recent vehicle scrappage policy that was instituted by the government, that is having high hopes for a steel sector, because there is a lot of formalized scrap recycling sources that will be made available by way of the vehicle scrapping centers. And then it's going to be formal, it's going to be higher quality of steel that is used in automobiles. And that means that the logistics and transportation will also be cheaper and more efficient. So this is how we are looking at it right now in terms of augmenting scrap supply. And an important point to note is that because it's scrap and because it's electric steel making, all of the emissions are scope 2, which means that they are not directly produced within the plant itself. Only a small amount is. And so because most of it is scope 2, most of it can be mitigated if those industries receive renewable power. So this seems to be the most simple route to produce clean steel, which is to take steel scrap, recycle it with RE, and produce clean new steel. However, the challenge here would be to get that level of supply. So now we have 3 questions in the end. Overall, how are we going to grow? Is it going to be using existing technology, Or are we going to build gas-based capacity and switch to green hydrogen later? Or are we going to prioritize scrap-based steel? Here, I mean, if we look at the first point, most of the new capacity that is going to come in is going to come in based on coal-based capacity. This is what we have come to know from industry. This is what we have come to know from various stakeholders, is that because of the issues with availability of natural gas, the prices of natural gas that are prevailing currently, industries are saying that they can't produce competitively priced steel using the gas-based route right now. And even though it might be great for the future in terms of easing their transition, today's demand and today's market still influences today's decisions. That's what I can say about this. And so because we are going to expand using coal, we will soon have 250 to 300 million tons of capacity that will be running on coal. That means that much more reliance on a CCUS ecosystem that doesn't exist. So if this is the way that we are going to go, we have to urgently develop CCUS policy for the country, urgently develop indigenous technologies for carbon capture and utilization that do not rely too much on imported technologies that drive up costs. And we need to be aware of the fact that RE, alternative fuels, and energy efficiency, while they don't individually do that much in terms of reducing the emissions, are collectively very important for at least dealing with half of the emissions that are coming from this technology. And this is not even delving into the issues regarding coal supply, coal quality, iron ore supply. I'm not going to comment on those things at this stage. The second route, I mean, as I said, it's a proven technology. The technology exists right now, and it's easy to switch from gas to gas. But gas prices are too high, and very few industries are thinking about taking such a medium to long-term risk when the current day market is already very competitive. However, we have to recognize that the longer-term future is more secure, and we also have to take into context all of the regulations and global policies that are coming in terms of decarbonizing hard-to-abate industries. So steel sector is going to be a focus for decarbonization. It is going to be a focus for border adjustment mechanisms like CBAM. It is going to be a focus for non-trade barriers. So there are going to be measures that influence global trade that are not necessarily going to be based on financial or emissions metrics. There is also going to be restrictions based on sourcing. They could say that if it's a fossil-based, if it's using coal, then we don't want to import it. All these things are coming in. Not to mention the Indian carbon market that is coming in. Again, a lot of hope pinned on that. So if the carbon market comes in and there is a national price for carbon, then you don't want to be stuck in the year 2055 with a coal-based plant struggling to switch it to CCS, which will potentially still be expensive. Not to mention, we don't know whether CCS will even be reliable in India, depending on how the geology is. And the third option, again, definitely is the simplest and the most promising option for producing clean steel in the country right now. But we are a growing economy, and we do foresee significant growth in steel demand over the next few decades. India is still only consuming about 80 kilograms of steel per capita, whereas the global average is around 120 or something, if I'm not, or 220 if I'm not wrong. So there is substantial scope for growth in steel demand in the country. So that means that because our consumption far exceeds our waste of steel, there is not going to be enough steel to produce to recycle and supply the entire market. Also, because recycling is currently done mostly by MSME sector, you can't hinge on them to switch to RE because the costs are too much for them to bear individually. There needs to be some amount of government policy and some amount of collective action that can be enabled such that they can all switch to a cleaner source of electricity. Right now, they are pretty much dependent on the grid going clean. So that's where we stand right now. And if you ask my opinion, I would say go 3, 2, 1. So prioritize scrap routes, first thing. Increase our shipbreaking capacity, increase our vehicle scrapping policies, put them into action, improve our logistics and transport for scrap, and provide incentives for recycling scrap and producing green steel such that it kickstarts a market for green steel in the country. Number 2, if you're going to produce virgin steel, produce it using gas-based technology. That's because in the longer term, that's what we need, and that's what will enable sustained production of our industry without grossly affecting its global competitiveness. And lastly, go for CCUS because, as I said, not a proven technology. We don't know the economics of it. We don't know the reliability of it. We don't know whether we can put that much CO2 into products. We don't know if there's a market for those products. So if we're going to do it for do CCUS, I would say do it only for the existing plants that have a longer life left, but no, don't build new coal-based capacity. If we can avoid it, we should avoid it. I mean, that was the end of my presentation. We have a bunch of reports that we have done. All of our work at CEEW is usually public facing, and we have very detailed reports where we talk about our methodology, talk about our assessments, why we say what we say. And we provide detailed policy recommendations for government and all stakeholders involved, including industry. I would invite you to check out probably these 3 publications that are most relevant to what we spoke about today. And please reach out to me in case of any questions. This is my email address. And thank you very much for your attention.
Thank you, Sabarish. I think that was a wonderful presentation, as all of us will agree. I think the most key takeaway points are quite evident to all of us. The way forward has been charted out on the 3-to-1 route, where I feel, in my own view, that the costs are going to be the most serious barrier. And I think you mentioned that we're looking at a $30 billion load on just on the capex itself. Unit prices will be about $2 to $3 billion a year. All of this is going to push up steel prices. But nevertheless, I think the more important point is that if India is to remain relevant in the global steel market and be a responsible player in this business, particularly with the new legislations in the European Union, the CBAM mechanism, eco design, and this digital material passport and all of that coming in. Some of that will be implemented over the next 3 years. Certainly, the Indian steel industry will have to look inwards and see what can be the best way out so that the Indian steel industry flourishes, and at the same time, not at the cost of environment. So I think this is where we are. And we'll have some questions at the end of it. There are quite a few in the chat box already, so we'll leave that till we move till we hear Dr. Sara for presentation. So may I request Dr. Sara, ma'am, if you could kindly make your presentation, and you have the screen with you. The floor is yours. Thank you.
Didn't come through, did it? Okay, is it on screen for you now?
We have your presentation on screen, Dr. Sara.
Okay, and I'm unmuted too. Good. Thank you very much for the kind introduction earlier, Commodore. I'm going to rapidly go through the slides that are here because it's way in excess of the amount of time that's allotted, and some of the information I'm going to present has already been spoken about. As we all know, the International Energy Authority, IEA, in Europe has projected the new future to be hydrogen DRI melting in an electric arc furnace. But there are some major challenges with that, which I will go through, and look at some other defossilization options for the brownfields, and look at some of the new innovative technologies coming up before I summarize. We all know that we've got a problem meeting the 1.5 degrees C. Last 2022 over 2021 increased the CO2 equivalents by 5 gigatons. And most of that, 82%, was coming from coal, oil, and natural gas combustion. China, of course, is the largest problem because of the intense blast furnace usage. USA is second, and then EU and India at 7%. We, as a steel industry, have the second lowest carbon intensity for metals production. The major emissions are predominantly from the blast furnace at 1.3, then the coke. Third is the electric furnace at about 0.24. The question has become whether the blast furnace will convert to EAFs, and will there be a variability around the world, which has to be because of the infrastructures throughout the world, and whether we need to decouple the iron making and the steel making. This is just a 2023 world steel production from the World Steel Organization. The red is the BOF blast furnace, BOS route. The green is the electric furnace. The black line is the tonnage from each of the countries. We all know China produces the most. It's actually dropped to 54% from 57 in 2021. The greatest impact is going to be addressing those people that have over 60% or even 50% blast furnace use in the countries. The Paris Accord is demanding 0.2 tons of CO2 per ton of steel by 2050. We're now at about 1.7. We've already seen the 7% greenhouse gases, 11% CO2 coming from the steel industry. Blast furnace is 92% of the greenhouse gases from the steel industry. It's only producing 72% of the steel. If we look at the strategy of 2070 for the IEA, they're looking at 95% hydrogen DRI, but the problem becomes the build rates, sorry, the sourcing of the green consumables, prime scrap availability, and the DRI ore quality. We're also going to have big problems with zero carbon DRI in the arc furnace, which is inherent with 100% hydrogen, the lack of CCU tonnages throughout the world, and the geographical availability of actually sequestering it, and the socioeconomic impact of closing blast furnaces. This is a chart I put together a couple of years ago, and based on 50 years production of DRI from the shaft furnaces, or from DRI production generally, the average per annum is 2.08 million tons of DRI plant construction. And if you look at 2050, according to the IEA, we're going to need 411 million tons of DRI. 213 of that will be hydrogen-based. And if we look at the 0.113 million tons of hydrogen per DRI plant, we're going to need 692 terawatts of power to produce the hydrogen. And that's 1,240 20 megawatt PEMs per year construction. And added to that, if you go the extreme and put 80% zero carbon into the electric furnace, then you're going to need another 370 terawatts of power to actually melt the stuff. We need green hydrogen, we need energy, carbon replacement, and prime materials. And the economics of hydrogen use in steelmaking, we need to see the hydrogen less than $2 a kilogram, and it's now between 3 and 8, depending on which part of the world you are. And we need energy to be much, much less than $20 per megawatt. Production is insufficient. By 2050, with a 213 million tons of DRI, we need 11.5 million tons of green hydrogen. And in 2022, only 0.11 million tons were green. And that was a 44% increase year on year. The figures for 2023 production of green hydrogen, I couldn't find anywhere, but the electrolyzer capacity had doubled to 8 gigawatts. In December of 2023, 45 million tons of clean or green hydrogen projects had been announced, but the investment was $570 billion. 100% efficiency in terms of hydrogen production is 39.4 kilowatts per kilogram, but in reality currently we're looking at anywhere from 50 kilowatts to 65 kilowatts, which is a 27 to 65%. Excuse me. In terms of energy, a great source is this global energy monitor. And I'm sorry you can't see everything underneath our pictures on the right. What I did was take their energy monitor graphs, and then I superimposed the actual production in 2022 and 2023, so you can see the difference in terawatts that were produced by different methods. Basically, if we go green in the industry, especially the electric furnace, we will save up to a kilogram of CO2 per kilowatt used. And if you look at the total energy excuse me, that was produced, excuse me, I'm losing my voice. In 2022, we were looking at 179,000, almost 180,000 terawatts. And they announced 60 gigawatts of green capacity coming on by 2030. Renewable energy was only 29% that year. 2023, the renewable energy increased slightly to 30%. But in 23, the renewable energy was down slightly because of the drought in China. The current capacity has reached, additional capacity reached 0.5 terawatts. There's not enough green energy at the right price. We need a 50% reduction in the pricing. That we need a $2 trillion investment in renewable energy, and we're going to need 2 terawatts for every 2.5 million tons of steel per year that's produced, basically. And if we look at the 67% efficiency of production, we're going to need almost 19% of the total world energy just to deal with the hydrogen requirements for the steel industry. Carbon substitutes, we're looking at 95% efficiency of the carbon that's contained in either pig iron or DRI as it comes into whatever melting furnace. We need that carbon currently for chemical energy, for the foamy slag production, and for recarburizing in certain circumstances. People are looking at replacing it with biochar, with plastics, with rubber, municipal waste. Firstly, there's not going to be enough sourcing for that. But also, most of the research to date has shown that you need carbon injection with whatever the replacements are for it to work in an electric arc furnace. In terms of the CCU capacity, it will address 54% of our hard-to-abate fumes. However, it's a relatively high conversion cost because you need carbon-free hydrogen to chemically stabilize the CO2, and the fixation is limited. Sequestration, as we've already heard, is geographically challenged. And if it's not mineralized, it's going to be temporary. The end users are predominantly food and chemical and the enhanced oil recovery industries. And they can't use all the CO2 that we could convert, so we need to find other uses. One question I have asked a long time ago, we had done a lot of work putting CO2 in place of argon and nitrogen in various steel mill and other non-ferrous applications. And we found it to be very efficient in terms of inerting, stirring, and even in an AOD vessel. So that's an option for using the CO2. Excuse me. Ore quality is another big issue for the world. Only 3 to 4% of the DRI is greater than 67%. The quality is deteriorating. The iron's already dropped 2%. The silica and aluminum's increased 2%, and the phosphorus going up by 2%. Upgrading the Pilbara oils in Australia, and Australia is the largest producer, as you can see from the graph at the top there, is an issue. So they're looking at redirecting it potentially to a submerged arc furnace and then on to the BOFs. Excuse me. There's an increasingly low availability of lump ore. And a lot of people are now restricting the ore to their own internal markets. The other option, of course, is to develop new process routes for the beneficiation of the ores. Swinburne University and Sara in Australia have looked at this, and they've developed a pilot, well, actually a lab-based looking to be a pilot place of flux magnetite pellets, which reduce the cost potentially of processing. It reduces it by one step, and it also does the magnetite processing at a lower temperature than normal. The graph in the middle there is just an example of the cost break even for the submerged arc furnaces and the electric arc furnaces below 67.5%. In this case, it's SAF, and above it's EAF. Scrap, we've already talked about scrap quite a bit. Most of the product issues ultimately can be traced back to the melt shop and the scrap quality. And the scrap quality will define the amount of OBMs that are required in a furnace. And the little chart at the top here shows that the need in the US predominantly for the good quality DRI, HBI, and scrap to make auto sheet. The continuous recycling of scrap is going to be a big problem because it's going to increase the copper significantly. We've already seen an increase of 0.12 from 82 to 19. We can shred the scrap to make sure that we remove all the copper coming in from the auto scrap. It also densifies it and cleans it up and gives us a better yield. One of the issues I have complained about many, many years is that scrap is not sold to exacting qualities such as the ore is, and we need to motivate, in North America especially, we need to motivate the scrap dealers to guarantee quality coming in. I've seen a lot of problems in furnaces where the mix has been back mixed to give a standard quality, and it's caused problems in the furnaces. So we also need to have a continuing analysis of scrap coming in. We're going to use a scrap-based process. And we need to look at reducing the residuals somehow. There's a company in Canada that's looking at chemically reducing the copper, but it's still under development. Or we need to look at new steel grades that are oblivious of the detrimental effects of these residuals. Arc furnaces, as we all know, operate with a high chemical energy input, and the little chart here on the right shows that 23% of that comes from carbon. It promotes the FeO reduction in the slag and in the DRI, and it creates the foamy slag, and all the benefits are actually there. If we have zero carbon coming in from the 100% DRI, we're going to have some major challenges. Without the chemical energy and the chemical carbon reaction capabilities, we're going to have incomplete reduction of the FeO, going to have less metallization, we're going to have more gangue in the furnaces. If we have lower carbon steel, we're going to have more FeO slag and lower yield. We're going to have higher temperature of melting. We're going to have more electrode wear. And when we're injecting carbon equivalents, we're going to have twice as much to inject because of the efficiency being lower. And we're going to need to redesign the refractories in the arc furnace because the carbon in the bricks that are current are going to be basically dissolved. There's going to be slag erosion. We're going to need a much deeper bath for the chemical reactions to take place. We're going to have more slag formers. We'll have more disposal weights. We're going to need to stir the bath because it's going to be too deep for the electrodes to the energy to stir them. So we're going to have plugs, tweers, injectors in place. But we also, again, could use CO2, which would reduce the need to make the argon and nitrogen. All of this is going to lead to a higher cost, yield, and productivity losses. And it'll be compounded by the lower quality ore that's available out there right now, and it'll increase the carbon footprint. Transition costs are exorbitant. There's some numbers here from Arcelor, POSCO, Thyssen, and Algoma Steel. I calculated from the IEA's own numbers that the cost of liquid steel would be $1,327 a ton. And the CRU actually quoted to crude steel product $3,700 per ton if we went the way they wanted to go. And that would make us not competitive worldwide. If you skip down below the 2021 and 2022 comparisons, I put 2024 numbers there. The USA is currently producing hot roll band at 839, Western Europe at 680, world exports 580, and China is at 448. So the competitiveness is going to be a big problem if we don't have taxes in place for the dirty steel coming in from China, for example. And then there's additional costs for the blast furnace and closures because of the downsizing and social implications. Now, if you look at the global steel tracker, it's been obviously observed because there's a lot of blast furnace orders and relines going ahead. This is just showing a chart of the different research areas that are being looked at, the electricity, the carbon, and the hydrogen, and different projects are assigned in here. Basically, it's biomass, CCUs, hydrogen reduction and production, electricity. They're also looking at upscaling the old non-steel technologies, the SAFs and the OSBFs and bringing induction furnaces up to mass production, which I doubt will happen. The challenges are increased energy, the scalability, which is a big problem, timeliness to market, and we've got an issue with the Chinese techno-economic advantage for hydrogen and green energy. But we could also look at modifying our brownfield operations would be less impactful for the socioeconomic issues. The blast furnace iron making, we talked about best available technologies. We could intensify the metallics use, which would particularly mean scrap and HBI into the blast furnace. They've seen reduction in coke, they've increased productivity. We could look at biochar substitution for the coke and PCI, hydrogen partial replacement of the natural gas or the hot blast to the furnace. And Hatch has predicted with PCI at 35 kilograms of 900 degrees C hydrogen that you can get 20% reduction in CO2, an increase in energy in the steelworks, a further 100 kilograms of coke reduction, but it's obviously going to be very costly. And adding to that, top gas recycling and CCUs, excuse me, you get an 80% reduction further in CO2, which would put the tons of CO2 per ton of liquid steel close to that of the electric arc furnace and probably twice that of the potential hybrid hydrogen DRI route. They found that pellets, of course, will reduce the CO2 by 85%. And the Japanese, with their Course 50 program, have got 30% CO2 reduction improvement using hydrogen, coke oven gas, and CCUs, and they're aiming for 50%. At the bottom there, Kobe Steel has reached a record for coke at 239 kilograms of coke per ton of hot metal by using 20% lump, 80% self-fluxed dolomitic pellets and PCI at 220 kilograms per ton of hot metal. Increased scrap use again in the BOF. There's two charts on the right-hand side from Swinburne University. They've been doing some work on increasing the amount of scrap used in the BOF. The current world is 17%, and in actuality, in the past, 45% has been used, but wasn't sustainable because of scrap. Their program was built on actual data from the steel mills, and for 35% scrap charge, they had a heat loss of less than 0.9%, but with the 10% scrap charge, the heat loss was 6.75. Obviously, for the future, looking at using more scrap would require smaller pieces of scrap, potentially preheated and continuously fed to the BOF. If you look at increasing the PCR from 10 to 30%, which is the bottom chart, and the increasing scrap from 22 to 28%, which is the dotted line going upwards, you can decrease the global warming potential by 10%. And also HBI in the BOF is going to have a higher cooling intensity and productivity impact. Electric furnace, green energy is the key. We've already talked about that. 2023, we could have saved 212 million tons of CO2 a year just by going electric for the arc furnaces for the world. If we go with 100% scrap, as shown in the middle chart here, you're melting with renewable energy, you're down to 0.1 tons of CO2 per ton of steel. Any use of the OBMs will increase that. The maximized benefit is obviously to use 100% scrap if you can get the quality. And then, as I said earlier, pay for quality, improve your yield. You can also use a preheated combustion air. We used to have a system when I was with Air Liquide, and we saw reductions from 480 to 280 kilowatts per ton. And the meltdown time came down 16 minutes using preheated air or oxygenated air. Hydrogen substitution, of course, in the oxy-fuel burners is an opportunity also to reduce further, but that's minimal amount of power compared to the power reduction. And the other big issue that I have is a lot of steel mills are not using value and use of the materials that are going into the furnace. There are programs out there that will tell you what scrap mix needs to be with pig iron or DRI to give you the lowest cost liquid steel. Off-gas analysis is another biggie. It will reduce your off-gas losses and balance your furnace for an improved combustion efficiency and operation and minimize your carbon footprint. And the other big issue is the control level that's on the furnaces needs to be level 2 at the minimum. Quickly for some of the new technologies that are out there. Calix is a new one in Australia. It's fines based, it's indirect heated, and they only use hydrogen for reducing the fines. They do it less than 100,000 degrees. They've got a study currently for a 30,000 ton a year demo plant. They've only been in being 2.5 years. They've done incredibly well with what they've got. They're testing the Australian ores because they are lower quality, trying to upgrade them. They have a steel process that they can feed to, and they also have this lilac kiln, which is a zero CO2 lime kiln. And basically, they're looking at converting the Australian exports from ore to HBI. I'm about to lose my computer because it's not plugged in. I'm sorry. Oh, come on. It won't allow me to do anything at the moment. Okay, let me get these. Sorry about that. I'm having trouble with my computer battery failing. I had forgotten. The other two technologies that are biggie right now are the Electra, which is they're producing 1 meter square, but I don't know what the thickness is, iron plate using electro-hydrometallurgical processes. They think they're reducing the CO2 by 90%. They can use low-grade ores below 55%. Boston Metals is an MOE using, again, a wide range of ores, processing temperatures of 2,000 degrees. They're limited by the Faraday's law for the productivity per cell. They have some major critical factors in there. The voltage is at 20 still, and they need to be at 5. They have an anode that's currently 6 carbon anodes. They hope to change to ferroniobium, but they haven't done that yet. Government has funded them a new plant to make the anodes, but they haven't done the work. They haven't done the research yet. The big issue is going to be the 400 cells will be needed to produce what they're now saying is 500,000 tons of steel a year. Originally, it was 1 million tons. We have the high 4 process by Prime Metals, fluidized bed using preheating, oxidation, and reduction. It's a 900 degrees C. They are supposed to have a industrial process going into with Fortescue metals and putting it to an electric melter. But the question now is whether the downsizing of Fortescue is going to compromise this product, this pilot. It's cost effective again, like Calix, because there's no pelletizing and sintering. Hybrid, of course, is the most well-known new process of hydrogen DRI EAF steelmaking, green energy. They're putting a 1.3 million ton plant into Gällivare in Sweden. It'll be up and running by 2026. They have proven this lined rock cavern storage for 100,000 cubic meters of hydrogen at 250 bars. But in future, they're going to need 120,000 cubic meters, which will represent 100 gigawatts of energy, which is enough for 3 to 4 days of operation. There's no real technical data out there other than they've actually supplied customers with green steel, but there's no information on how the plant operated. They do say that they reckon it'll reduce CO2 by 30 to 50 million tons a year. Induction furnaces were mentioned. We're looking at probably 1 million tons max per year for plain carbon steel because of the lack of refining, although it could go to a secondary metallurgy system. The arc furnaces use more total energy, but less electrical. And one big issue with the induction furnaces going to a larger production, of course, is going to be the need to change the furnace lining on a regular basis because it's much thinner to start with and it will wear much, much quicker. So in summary, the need for defossilization has spawned a lot of innovation. The question is whether the new technologies will be timely enough but we're already behind this 1.5 degrees C goal. Hopefully some of the known technologies that are non-ferrous can be upscaled for us, but that's questionable too. The hydrogen DRI EAF steelmaking is the cleaner technology, but providing the green consumables and dealing with the cost has become a problem across Europe. And some of the plants already are at the point of deciding they will not convert. There's more solutions with the brownfields, maximizing metallics use in the blast furnace and the BOF, using the best available technology as has previously been stated, trying to find coke or carbon alternatives, and with the EAFs, convert to green energy ASAP and maximize the arc furnace scrap use rather than the OBM use, and process the scrap in-house. You have control of quality, you optimize your charges using the programs, and you use off-gas analysis and value in use to operate the furnace efficiently. Thank you very much. That's the end. I'm sorry to have taken so long, but it is an exciting time to be in the industry, and thinking outside the box is going to be a great way to solve problems for the future. But there's a great statement here from Joachim von Schiele, who said decarbonization without green power means deindustrialization, and I think he's right. Thank you for your attention.
Thank you, Dr. Sara, for that wonderful presentation. I think you covered a wide range of issues in the short time that we have had. But I think it's important to understand some of the key issues that you got out, particularly the ratios in terms of blast furnace and BOF route. 92% of GHG emissions, but producing 72% of steel, and 87% for the electric arc furnace route, doing 28% of steel. That's a phenomenal number. What is very interesting is to also see from an industry perspective, to see how steel prices might go if as a forecast. You have put some numbers there from IEA and CRU at 1,327 and $3,700 per ton. That's a huge amount of money price to pay, but obviously the downstream impact on the rest of the industry, which are consumers of iron and steel, will also be impacted. The other thing I thought that you had brought out very clearly was this wide field of expertise in different parts of the world, which is working on different options for defossilization, as you call it. And there have been some very interesting examples that you quoted. I particularly liked your Japanese Coast 50, where they seem to have got some success. And the hybrid project in Sweden is very closely guarded, the first RE plant with hydrogen, because they're going to need 100,000 cubic meters of hydrogen to do this. Then it's not easy to be in Sweden to get that, even if they use renewable energy. There are plenty of wind farms and all of that, but to get all that amount of green hydrogen is not going to be easy. So what I can see here is that probably there will be, if hydrogen is to be used in many of the economies which are looking at hydrogen as the route for going green, will need to are actually those economies which don't have the potential to produce hydrogen through the renewable route. Much of that is in the tropical areas where wind and solar signatures are better, hydroelectric power is better. So there will be some new issues there. But thank you very much for your presentation. I can ask MRAI to get this off the panel so we can get back to some questions. There are some questions which are in the chat box. If I might start with a few. The first question, of course, is that, if the whole world is moving towards, or particularly India, and that has been brought out by Sabarish, I think this is the question for you. If there's going to be such a lot of investment into coal-based steel capacity, I don't know what is the ROI on steel-based plants, new plants that you get, and what would be the payback period for that investment. Given the situation that you brought out and the emphasis that there would be additional investment for, if nothing else, as per the graph that you showed on carbon capture and utilization being the major sort of line item that could make the impact. So the question is, how do you see this? Do we see much of our coal-based steel capacity floundering in 20 years from now, 10 years from now, 30 years from now? Of course, from an Indian perspective, we have said this in different platforms of common but shared responsibility sort of approach. But nevertheless, there's a substantial amount of investment being planned here. So maybe is there a need to intervene there? And here, Dr. Sara, you might also like to chip in to see how other countries are looking at additional coal-based steel capacity, and whether they are also sensitized to this fact that that these coal-based plants may not be viable from an economic or a technical or from a socio-logical perspective. So first, Sabarish, if you can make some comments, and then I'll request Dr. Sara to respond to this, the first question that we got in the chat box.
With regards to whether these plants will suffer 20 years, 30 years later, I think the simple answer is it depends on how serious we are about our decarbonization targets. It depends on how serious we are about maintaining our, as you said, common but differentiated responsibilities, but responsibilities nonetheless that we have committed to in the global front. In terms of market pressures to decarbonize and how that will affect coal-based steel capacity in the future, we talk a lot about CBAM and foreign regulations, but an import regulation like CBAM is unlikely to affect the Indian steel industry that much, because I think the value of steel exports as a part of our total exports is only 3% or something like that. It's not that much of steel that India exports. Steel products that use steel, yes, but then it depends on how the EU is still deliberating on how to define, component mix of a particular product. I mean, if we export a car, are they going to tax it based on the amount of steel that is used? I don't know if they have made a decision on that yet. So until such decisions are made, it remains to be seen how a CBAM could affect the market. Beyond that, I mean, we're talking about the Indian carbon market. So when an Indian carbon market comes in, it depends on how robustly it is designed. It depends on how many sectors are involved right from the start, such that there's an active market for the certificates that are traded. And it depends on how the sector level emission caps are set, such that the mechanism works efficiently. So it's still, I know it's a lot of depends, but I think it's a little early to say whether it's going to be a problem or not. But for sure, considering our commitment to net zero, considering our timelines, it is going to be a challenge for coal-based plants in the future. Because a CCUS ecosystem is not under the control of a steel producer, right? You can't be a steel maker and then 40 years later say, I'm going to put CCS right now, because you need to build pipelines, you need to have only the capture part is pretty much under the control of the steel plant. Beyond that, with transportation and sequestration, a whole other entity, a bunch of entities need to align on the cause and put in the investment. Carbon capture use, yes, but there are a limited number of products you can produce from CCU right now, and they are much more expensive than their market counterparts. And if the entire 300 million tons of CO2 emissions coming from the steel industry, if all of that is converted to CCU products, how much will the value of CCU products go down, because there's so much supply that's coming in, right? So that's also a challenge. And I would also like to touch upon the point made by Dr. Hornby on the issues with HDRI as well, right? So you need to have higher grade iron ore. You need to have pelletization facilities in order to supply pellets, because the shaft furnace does not take lump ores or fines, it takes pellets mostly. I mean, that is also a challenge that we have to navigate. But I have a counterpoint to that, in that if we continue with the coal-based route, that's still a challenge, as I responded to one of the questions there, because the BF-BOF industry imports around 80% of its coking coal requirement in India, right? And of that, most of it comes from Australia. So it depends on the politics in Australia for that to for us to say whether it'll affect us or not, right? So if there is a Green Party in Australia that's elected, let's say 10 years later, that says we are going to put a moratorium on coal mining and exports, how will that affect India's industry? Do we have enough alternative options for export countries to look to immediately? We need to really think strategically about how global policies are going to affect our industry and whether they will and to what extent. That would be my answer to that question.
Dr. Sara?
Excuse me. I think what Sabarish has said is quite true, and I think looking at the world, we're going to see hopefully a better collaboration, and we're going to see decoupling of the iron making and steel making. I think that has to be. We're going to have to use the facilities. I mean, MENA is heavily using their solar capacity to make energy and store energy for use there, and they're converting their steel mills. Some of them have got extensive solar panels on the roof of the steel mill shop to actually capture the power, and they are storing it. In Australia, they have a lot of untapped hydro and potential solar power. They need to be able to capture that. They have a lot of ore, and the question there becomes whether or not the ore mining companies wish to, how can I say this? My impression is that they're paying lip service to upgrading the ores, that they have the world by the supply and demand scenario, that they have to buy the ores, and they have to accommodate the lower grade ores rather than the Australian ore miners putting a lot of money into upgrading the ores, which in some cases is very difficult anyway. I think if I was them, I would be putting funding into the processing the ore that they have through a shaft, which is not a problem. The problem becomes putting it into an arc furnace. So sure, put it into a submerged arc furnace and make either hot metal or pig iron. Hot metal for the local mills, pig iron for export. So I think that needs to be seriously looked at around the world. I mean, there's a couple of mills going into Sweden that are going to produce the iron and export the iron because they do want to decouple. So I think that is a way of the future. Hydrogen also, they're talking in some countries of producing the hydrogen and transporting it, exporting it to other countries to use. I mean, everything that's going on right now is heavily pushed by the European community because Russia's basically got their finger on the button for the natural gas. So the Europeans have to find a solution that isn't based on natural gas technology. The Global Energy Monitor is really an interesting program. And I didn't have it in here, although I've used it before. The map shows all the steel mill projects that are ongoing, that are under construction, that have been cancelled. They also have one for hydrogen, so you can monitor the hydrogen programs as well, all the hydrogen projects that are going on around the world. And the ones that have, there's an amazing number of electric furnace DRI and hydrogen projects that are not getting off the ground.
Very quickly, I just thought that Dr. Sara, if you could just elaborate on that among the lists that you showed, the two of them were very interesting. One was, of course, hybrid in Sweden and the Japanese Coast 50. Could you expand on that just a little bit more and see how developing economies or India and the other people in the ring can benefit from this, or is it still a very guarded technology, or ultimately it's for the common good? So I would think that that there should be some way by which these technologies should percolate down to other steel manufacturers so that the overall burden on planet Earth is reduced. So if you could say a few words on
the Japanese Course 50 program, they have written a lot of papers on it, and they actually have in in the Elliott lectures that I'm giving, I actually have the course 50 diagram. I didn't have it in here, but they have a complete layout for the course 50 program on how they're going to make it sustainable and circular. And they're using everything within the steel mill to put back into the blast furnace and generate electricity. I mean, it's truly circular. They've done the work so far on a 12 cubic meter pilot, but they're putting it onto larger ones now. It's very successful, and their plan is to share the technology that they're developing. The hybrid, they've been very, very quiet, even internal to their own companies, about the project, how it's gone, how the startup went. Rumor has it there were some issues, but we don't know whether it was the DRI plant or whether it was the DRI zero carbon going into the EAF. There's no information out there at this point in time.
Dr. Hornby, I have a question.
I think we are at the yes, please. Somebody's got
Just
a
a
question.
short
Yeah, go ahead.
question, Commodore Samaddar. I mean, like Dr. Hornby, you mentioned, upgrading of the iron ores, and that's something that, perhaps exporters are not doing just so that they can push more ore into the market. And if you look at the Indian iron ore mining scene, the primary amount of ore that we produce. And ores that are more than 65% is number 2 in terms of India's iron output. But the problem is that most of these are available as fines and not as lumps. And so what would you see as the role for beneficiation and pelletization in order to upgrade the ores to an HDRI standard? Is it like possible, or is it also fraught with a lot of challenges, or what would you say?
In terms of your fines, are you talking about there was a break in the communication there. Are you talking about whether your fines should be upgraded?
I think most of the iron that India produces, iron ore, has an iron content of more than 62%. But I think more than half of it is iron ore fines and not iron ore lumps, right? So what is the potential for upgrading and pelletizing the ores to bring it up to an HDRI standard of 67%? Is that like something that we should be really looking at, or is it like a moot point?
Well, I think at 65%, you could probably put it through the system anyway, but there are some fines technologies out there that you could be looking at that would use the fines direct. I mean, we could possibly have a separate conversation on that, but I would
definitely reach out to you on this.
A lot of fines. Yeah, I'm in the middle of writing the Elliott lecture for the 2024, and I'm looking at some of the other technologies that are available out there, other than the ones I just briefly looked at, including a lot of the fines technology like FINEX and FINMET and the FIOR. And, Calix has got a lot of potential for processing ore direct as fines.
So I think we are having some minor internet issues, and it's also time to wind up. So Ritesh Bhai, if I might request you to kindly
Yes, sir.
deliver the vote of thanks, and really grateful to our two speakers for sharing so much knowledge. Ritesh Bhai, the floor is yours.
Yes. Thank you very much, Captain Commodore Sujeet ji. Thank you so much, Zain ji, for this wonderful session. First of all, I'd like to sincerely express our heartfelt thanks and gratitude to our both eminent speaker, Mr. Sabarish Elango and Dr. Sara Hornby, ma'am. Thank you very much for joining us early or time. Both the presentations were very, very informative. And especially myself coming from the trade and industry, it's kind of an eye opener for us, and gave us a reality check where we are morning to evening. Now we are having this term of decarbonization, but it was very necessary for us to have that kind of a reality check, that where do we stand, what is the way forward. And I'm particularly very much intrigued by your presentation, Mr. Sabarish ji, and we would like to certainly listen from you much more. And ma'am, Dr. Sara, I think your presentation was full of very, very deep and technical insights. I think we need to sit with a couple of very good engineers to make more sense out of it, and how we can extract very useful information out of it. On behalf of President of MRAI and our entire association, we would like to deeply thank both of you, our eminent speakers, for sparing out time today. And we are looking forward to engaging with both of you in our new near future conferences in a more effective way, probably in the physical way, where you will also find many more questions from our very interesting colleagues who are ready to listen to you. Thank you very much, sir. Thank you, Zainji. Thank you, Commodore Sujeet. Thank you. Good evening. Thank you.
Thank you very much.
Very much.
Thank you. Thank you. Thank
Bye.
you.
Thank you. So this brings us to a close of today's proceedings. And once again, thank you very much, Zain bhai, Dr. Sara,
Thank you. Pleasure.
Ritesh bhai, and Sabarish. I hope to do more of these seminars and add more to our body of knowledge, particularly from such privileged speakers like you. Thank you very much. And again, good night and good day to whoever is wherever. And thank you so much. Thank you very much.
Thank
Very
you.
grateful.
Thank you for the invitation. Have a great evening. Bye-bye.
Bye-bye.